Dear friends, Schrödinger equations, which is the fundamental equation of the quantum mechanics, is a wave equation in the variable psi. Okay, this is the equation of the quantum mechanics in the same sense that like the second law of motion is the fundamental equation of the Newtonian mechanics. So you know very well a wave equation like curly to psi by curly x square equals to 1 over v square curly to y over curly t square. Now these equations governs a wave whose variable quantity is y and that propagate in the x direction with the speed v. In the case of wave in a stretched string, you know, y is the displacement of the string from the x-axis, and in case of the sound wave, y is the pressure difference, and in case of the light wave, y is either the electric or the magnetic field magnitude. So this equation, the wave equation, can be derived, you know, from the second law of motion for mechanical waves and from Maxwell equation for the electromagnetic waves. I'll take help of the wave equation for deriving the Schrödinger equations, okay? So let's accompany with me for that, okay? Now Schrödinger equations, the derivation of Schrödinger equations, wave equation, and time independent, because there are two types, time independent and time dependent, for a particle moving like a wave, okay? Now this is the wave equation, curly to psi by curly t square equals to v square curly to y over curly x square. Now for the microscopic, you know, bodies, for the microscopic particles or the bodies, like for microscopic particles like electron and protons, y is replaced by a wave function psi, where psi is a wave function. So we are getting an equation now. Now psi may be a function of x, y, z, like position coordinates. If psi is a function of only x, y, z, then the wave equation which we derive, that will be time independent. And if we consider the wave function which is also dependent on time, like the t is also a variable, then the equation which will derive, that will be time dependent. So because now in our case, now at present we are discussing time independent, so we'll consider psi which is only a function of x, y, z, but not that of the time, okay? So this is a wave equation. Now replacing here this y by the wave function psi, okay? So wave equation in terms of the wave function. So this is the wave equation, and you know, particle is moving along the x direction, and the particle behaves like a wave, and the equation is this. Now if we consider the three-dimensional, if we consider the three dimensions, then it becomes the right hand side, you know, this term becomes curly square over curly x square plus curly square over curly y square plus curl square over curl z square n psi. And this is called Laplacian operator, right? Now then Laplacian operator means del square. It becomes del square psi. So this is a wave equation, three-dimensional. Again, let the particle is moving along the x direction and we consider the wave equation, this wave equation, right? And this is second order differential equation. Second order differential equation. Then the general solution of this equation is psi is equals to psi naught sine 2 pi by lambda into x. So this solution is only position dependent and time independent. Lambda is a wavelength and x is the direction along which the particle is moving. Now differentiating with respect to x, both sides. So curly psi by curly x becomes sine of 2 pi by lambda. This is a differentiation. Differentiation of sine. Differentiation of sine becomes the cos. And because it is with respect to x, so whatever the term is attached with x, it comes in multiplication. Okay. And once again differentiating with respect to x, that becomes curly 2 psi by curly x square is equals to, now what happened, the differentiation of cos becomes minus sine, okay, and again this factor comes with the multiplication and it becomes square with negative sign, okay. Now look, psi naught sine 2 pi by lambda into x. This is here. And what it is? Psi. So this is replaced. This factor is replaced by psi. So the equation becomes curly 2 psi by curly x square is equals to minus 2 pi by lambda whole square and psi. Okay. Now using the de Broglie hypothesis, lambda is equals to h over mv and lambda square is h square over m square v square. Okay, and now you know half mv square is the kinetic energy. So lambda square becomes h square over 2m into kinetic energy. Now total energy is kinetic plus potential. Kinetic becomes total minus potential. Substituting it here, lambda square becomes, okay, and lambda square, substituting it here in the wave equation. So the equation becomes like this. Okay. Now you know h cross is h over 2 pi. So including h cross in the equation. So the equation becomes curly 2 psi by curly x square minus 4 pi square 2m e minus v is psi over 2m h cross whole square. Okay. Now certain term factor cancels out and we left this equation. Curly 2 psi by curly x square plus 2m over h cross square e minus v into psi equals to 0. Okay. Now for 3D, you know, for three-dimensional, this curly square over curly x square, it is replaced by del square psi into this equals to 0. So this is a very, very important equation. Time independent Schrödinger equation, del square psi plus 2m over h cross square e minus ve into psi equals to 0. Okay, always remember Schrödinger equation, time independent. Now if the particle is free particle means it is not bounded, it is not in a bound state. That means no potential energy. So potential energy is zero. So that becomes del square psi plus 2m over h cross square E psi equals to 0. This is an equation for free particle which is not bound, which is not in a bound state. Now we are coming time dependent. Time dependent Schrödinger equation. So we not consider this solution of this equation. Instead, general solution will be like this: psi equals to psi naught e raised to power minus iota omega t. Now this solution contains the term time. So time dependent means the solution which contains the term like time. Okay, let this is a solution. Now differentiating with respect to t, curly psi by curly t equals to, when we differentiating the term which is with time comes in multiplication. Okay. Now this is minus iota omega psi naught e raised to power minus iota omega t. Now what it is? Look, psi naught e raised to power minus iota omega t. This is nothing but psi. So substituting it here. So the equation becomes curly psi by curly t is minus iota omega psi. Now omega is 2 pi nu and u is h, e over h, e is energy, and it becomes e over h cross omega. So replacing omega with e over h cross, and e psi becomes like this. Iota square is what? Minus 1. So iota with iota square, with 1 iota it cancels out. So E psi becomes, okay, now already we are having time independent solution. Already I derived just before. Okay. Now here the term E psi, and we are having the E psi which is time dependent. Okay, so substituting E psi here, which is time dependent term. So the wave equation becomes now just rearranging. So very simple. Okay, just rearranging the terms. So this is an equation, very important. Okay, now this term represents to the kinetic energy and potential energy. So this is actually an operator which is called okay, We call it H. H is Hamiltonian operator. This is term like that of the kinetic energy, but don't think like in classical mechanics, which the kinetic energy of the classical mechanics, like P square over 2m, because in classical mechanics the kinetic energy cannot be negative. But this is actually, the whole, it is an operator, Hamiltonian operator. When this operator is applied to a wave function, then this operator extracts the energy from the wave function. And this is the energy, okay? Energy into psi. So Hamiltonian, this is Hamiltonian operator. When operator is operated on a wave function, it extracts the energy from that wave function, okay? So H psi becomes E psi. This is energy, E psi, okay? So this is very important. This is an operator which is operated on a wave function, and then it extracts the energy from the wave function, and that energy is E. So this equation is time dependent Schrödinger equation. Okay. Thank you.